Have you ever really stopped to think about how everyday things around us are actually put together? Like a big bridge or even just the swing set in the park. Underneath it all, there's this hidden world of, well, engineering. And today, we're going to pull back the curtain a bit on one of the most basic, but also really versatile ways things get joined, welding. Specifically, manual metal arc welding, or MMA. You might also hear it called SMAW, shielded metal arc welding. So we've done our homework, gathered up the sources, notes, all that stuff on MMA. And our mission today really is to cut through some of the technical talk, pull out the important bits, and give you a kind of shortcut to understanding how this works. By the end of this deep dive, hopefully you'll have a totally new appreciation for the skill involved.
Well, definitely. And it's got such a fascinating history, too. MMA welding actually goes way back, invented in Russia, 1888. But the really interesting part is, back then it was just a bare metal rod. The big step, the coated electrodes we use now, that didn't happen until the early 1900s in Sweden and the UK mostly. So yeah, it's old, but it's evolved. And it's still seen as, the most versatile welding process out there. Still incredibly widely used.
Okay, so let's unpack that. How does MMA welding actually, well, work at its core? Picture this. You have this coated rod, the electrode, right? And the metal part you want to weld, the workpiece. You touch them, strike an electric arc. And this arc is unbelievably hot. Our sources mention around 6,000 degrees Celsius.
Yeah, incredibly hot. Hot enough to melt both the tip of that electrode and the surface of the workpiece. They basically melt together, forming this little puddle of molten metal, the weld pool. And that heat does something else really vital. It melts the coating on the electrode, the flux. That flux coating, it's like a mini chemical plant. As it melts, it releases gases that form a protective shield around the arc and the molten pool. And it also forms a liquid slag that covers the pool. This protection is absolutely essential. It stops oxygen and nitrogen from the air getting into the molten metal.
Which would weaken the weld, right?
Exactly. It would contaminate it and make it brittle. So the gas and slag shield it. Then, as the mill cools down, that slag solidifies into this kind of crust. You actually have to physically chip that slag off afterwards to reveal the clean weld underneath. Oh, and one practical thing, because you're using these individual rods or sticks, you typically only weld a short length before the electrode is used up. So you stop, put in a new electrode, chip the slag maybe, and then restart the weld.
Right, a bit stop-start then. But despite that, why is it still so dominant, so versatile?
Well, the advantages seem pretty clear from what we've read. You can use it on most common metals, ferrous and non-ferrous. It can handle a big range of thicknesses, from pretty thin to very thick material. You can use it in any position, flat, vertical, overhead, horizontal, literally any angle.
Yeah.
And it's, well, reasonably easy to get the hang of for basic stuff, and the equipment isn't outrageously expensive, relatively economical.
All true, which makes it super useful in so many situations. So thinking practically then, what kit do you actually need? If someone wanted to try this, our sources list the main things. You need a power source. That could be a transformer, maybe a rectifier, or these days often an inverter machine. Then the electrode holder, the thing you actually grip the electrode with. Power cables, naturally. A proper welding visor or helmet, absolutely essential for eye protection. A power return cable, sometimes called the ground clamp, to complete the circuit. And of course, the electrodes themselves, the consumables. You also see specialized gear sometimes, like electrode holding ovens or quivers, to keep certain types of electrodes dry and warm.
Right. And talking about power sources, that's a key area. MMA is flexible. It can run on direct current DC or alternating current AC. So DC, think of it like water in a pipe flowing one way. It's got a direction, either positive or negative polarity. AC, though, that's different. The current reverses direction constantly, back and forth, really fast, like 100 or 120 times every second. And the machines that provide this power vary, too. You've got the old school heavy transformers, transformer rectifiers that convert AC to DC. For field work, out on site, you often see diesel or petrol-driven generator sets. Very common. And then the newer technology, inverter machines, which are much lighter and more compact. But here's the really crucial thing. No matter the type, the power source has to provide what's called a constant current output, sometimes called a drooping characteristic. Constant current. Okay, why is that so important? It means the machine tries to keep the amperage, the current, steady even if the voltage changes slightly, which happens as the welder moves their hand closer or further away. This constant current is what gives you a stable, controllable arc. It's fundamental to M&A.
Gotcha. So this power source, this constant current machine, what does it actually need to do for the welder? First, it needs that initial kick to start the arc, right? The open circuit voltage, OCV. Our sources say that's typically between 50 and 90 volts just to get the arc established. But then, once the arc is going, the voltage drops much lower for the actual welding, usually down to like 20 to 40 volts. It also needs to provide the right amount of current, the air bridge, typically somewhere between, say, 30 and 350 amps, depending on the job. And critically, it needs to maintain a stable arc that recovers quickly if it flickers for a moment.
And there's a safety aspect, too, that initial OCV shouldn't go above 90 volts.
Exactly. That OCV helps initiate, then the lower arc voltage sustains it during welding.
Okay, now this is where, for me, it gets really interesting, because the quality of that final weld, whether it's strong and reliable or not so good, it seems to hang entirely on to getting a few key things just right. These variables, we're talking current, voltage, travel speed, polarity, and even the specific electrode you choose. Absolutely. These are the welder's main controls, and mastering them is the real skill. Let's break them down. First, current, the amperage. Think of this as the amount of electricity flowing. It controls how fast the electrode melts the burn-off rate and how deeply the arc penetrates the base metal. Now, if your amperage is too low, well, the arc might be unstable, sputtery. You won't get good fusion between the metals, penetration will be shallow. You might end up with defects like porosity or slag trapped inside.
Right, not digging in enough.
Exactly.
Right.
But crank it up too high, and you've got the opposite problem. You get excessive penetration, maybe even burn right through thinner material. You'll probably see a lot of spatter little bits of molten metal flying off, maybe undercut, which is a grooves melted into the base metal alongside the weld. Also, deep craters when you stop.
Okay, so finding that sweet spot for amperage is crucial. What about voltage?
So voltage is more like the electrical pressure driving the current across the arc gap. We mentioned the OCV to start the arc, 50 to 90 volts usually. But the actual arc voltage during welding, that 20 to 40 volts, is directly controlled by the welder manipulating the arc length. That's the physical distance between the tip of the electrode and the surface of the weld pool.
Ah, so the welder is constantly adjusting that tiny gap.
Constantly. A shorter arc length means lower voltage. A longer arc length means higher voltage. And this arc voltage affects the heat spread and how fluid the weld pool becomes. If your arc length is too short, so the voltage is too low, you risk poor penetration again. The electrode might keep sticking or stubbing into the workpiece, you won't get proper fusion. But if your arc length is too long, voltage too high, the arc becomes, well, wild. Hard to control. You get excessive spatter, maybe porosity because the gas shield isn't effective over that longer distance. The arc might wander, and then the weld pool gets very fluid and difficult to manage.
Wow, that's a real balancing act, millimeter by millimeter.
It really is. And then you add travel speed. That's simply how fast the welder moves the electrode along the joint being welded. This, along with current and voltage, determines the heat input per unit length of weld. Go too fast, your weld bead will likely be narrow, maybe humped up, and it cools very quickly. This can trap slag or lead to undercut because the edges didn't get filled properly.
Like drawing a line too quickly with a marker.
Good analogy. But if you go too slow, you're putting too much heat in one spot. You can get what's called cold lap, where the weld metal just kind of sits on top without fusing properly at the edges. You also deposit too much weld metal, making a wide, bulky, irregular bead, and you can still get undercut if the pool gets too fluid and sags.
Okay, so current, voltage, speed, the welder is juggling all three constantly. But then there are choices you make before you even strike the arc, like polarity and the type of electrode. How do they fit in? They seem like big decisions.
Huge decisions. They fundamentally change how the arc behaves and the properties of the final weld. Let's take polarity first. This only applies if you're using direct current, DC. It determines where most of the arc's heat energy is focused. If you connect the electrode holder to the positive terminal on the workpiece to the negative, that's called direct current electrode positive, or DCEP, sometimes just DC positive or reverse polarity. With DCEP, about 2/3 of the heat concentrates at the electrode tip. This results in deeper penetration into the base metal.
Okay, so DCEP for digging deep.
Generally, yes. Now, if you switch the connections electrode holder to negative, workpiece to positive, that's direct current electronegative DCEN, or DC negative or straight polarity. Now, about 2/3 of the heat is in the workpiece, the parent material. This means the electrode melts faster, you get a higher deposition rate, but the penetration into the base metal is shallower. Good for filling gaps or on thinner materials, maybe.
So you choose polarity based on whether you need penetration or fill.
Largely, yes. One potential issue with DC, though, is something called arc blow. The magnetic field created by the current flow can sometimes deflect the arc, especially in corners or at the ends of plates, making it harder to control. Now, if you use alternating current, AC, the polarity is constantly switching, remember? So the heat distribution is basically even.
Mm,
Roughly 50% at the electrode, 50% at the workpiece. It avoids arc blow, which is one advantage.
right. And then the electrodes themselves, they aren't all the same, are they? You mentioned the coating.
Not at all. The type of consumable electrode, specifically its flux coating, makes a massive difference. There are three main generic types based on the flux chemistry. First, you have rutile electrodes. Their coating has a lot of titanium oxide, rutile. These are often seen as the general purpose, easier to use electrodes. They ignite easily, give a very smooth, stable arc, produce minimal spatter. The slag they form usually peels off quite easily, and they tend to leave a nice smooth weld bead profile. Good all-rounders, often work on AC and DC.
The user-friendly option, perhaps?
You could say that, yeah. Then you have basic electrodes. These have high levels of calcium carbonate and calcium fluoride in the coating, often called low hydrogen electrodes. They are the choice when you need higher weld quality, better mechanical properties, and particularly good resistance to cracking, especially on thicker or higher strength steels. Their slag is fluid but freezes quickly, which is helpful for welding out of position like vertical up or overhead. But the arc can be a bit harsher, they often produce a more convex, less appealing bead profile, and the slag can be really tough to remove. It needs proper chipping, and they must be kept dry, very sensitive to moisture pickup, which introduces hydrogen.
Okay, so high performance, but more demanding to use.
Exactly. And finally, cellulosic electrodes. These have a high percentage of cellulose organic material in their coating. This creates a lot of gas when it burns, resulting in a very forceful, deeply penetrating arc. They also burn very fast, which allows for high travel speeds, great for pipeline welding, for instance. They're known for being easy to use in all positions, even vertical down. However, and this is a big one, that cellulose decomposition produces a lot of hydrogen gas. This means the weld deposit has high hydrogen levels, which significantly increases the risk of hydrogen-induced cracking, especially in the heat-affected zone, the HAZ, of the base metal next to the weld.
Ah, so that cracking risk we mentioned earlier links back strongly to electrode choice.
Absolutely. Using cellulosics requires careful procedure control, especially on crack-sensitive steels. Oh, and a general rule, while most electrodes designed for AC can also run on DC, not all electrodes designed primarily for DC will run well, or at all, on an AC power source. You have to check the classification.
Okay, that makes sense. Lots of interacting factors.
Definitely. And if you think about efficiency, there's a term called the operating factor, or OF. It's basically the percentage of time during a shift or an hour that the arc is actually on and depositing metal. Arc on time. For manual metal arc, because you're constantly stopping to change electrodes, chip slag, reposition, the operating factor is relatively low, typically around, say, 30%.
Only 30% of the time actually welding.
Yeah, give or take. Compare that to a semi-automatic process like MIG or flux cord welding, where you might get 50 or 60%, or fully automated robotic welding, which could be up near 90%. So while M&A is versatile, it's inherently a slower, more labor-intensive process in terms of pure deposition rate. Productivity is lower.
That's a really important point for understanding where it fits in industry. So with all these variables, current, voltage, speed, polarity, electrodes, the stop-start nature, it seems like there's a lot that could go wrong. What are the common flaws or imperfections a welder needs to avoid? What happens when things aren't quite right?
Well, yeah, things can definitely go wrong. You see characteristic imperfections. Slag inclusions are pretty common. That's bits of that flux slag getting trapped inside the weld metal instead of floating to the surface, usually down to poor technique like incorrect angle or travel speed or not cleaning thoroughly enough between passes on a multi-run weld.
So trapped dirt, essentially.
Kinda, yeah.
Wow.
Then there's porosity. These are little gas bubbles trapped in the solidified weld. Looks like tiny holes, often caused by moisture, maybe damp electrodes, especially those basic low hydrogen ones if they haven't been baked properly. Or could be contamination on the base metal, like oil or paint.
Okay, what else?
Lack of fusion or lack of penetration. This means the weld metal hasn't properly fused with the base metal or hasn't penetrated deep enough into the root of the joint, usually caused by incorrect settings, amperage too low, travel speed too fast. Maybe the joint preparation itself wasn't right, like the root gap was too small.
Oh, a weak joint, basically.
Potentially very weak. You also get undercut, which we touched on. That groove melted into the base plate alongside the weld toe, often from having the amperage too high or incorrect arc length or travel speed. It creates a stress concentration point. You might also see arc strikes. These are little accidental burns on the base material away from the weld joint, caused by carelessly striking the arc. Bad practice shows lack of skill can sometimes initiate cracks. Poor grand clamp connection can contribute too. And finally, the really serious one, hydrogen cracks. These can be tiny, hard-to-see cracks, sometimes appearing hours or even days after welding, directly linked to hydrogen getting into the weld, often from the electrode coating, like cellulosics or improperly handled basic types, moisture or contamination, combined with stress and a susceptible microstructure. Very dangerous.
Right, that sounds like the most insidious one. So much depends on controlling that hydrogen.
It's critical for high-integrity welds, absolutely.
So listening to all this, it really hammers home one point, the human element. You can have the best machine, the perfect electrodes, but at the end of the day, making a good MMA weld seems incredibly dependent on the welder's actual skill, their feel, their intuition almost, especially that constant adjustment of arc length to match how fast the electrode is burning away.
You've hit the nail on the head. That's the crux of it. The skill factor in MMA is very high. So to kind of sum up the pros and cons, advantages. You can use it almost anywhere, field or workshop. Huge range of available consumables for different metals and needs. Works in all positions. Equipment is relatively simple, portable, and less expensive. Disadvantages, that high skill factor required. Potential for defects like arc strikes and slag inclusions that need care. The low operating factor, meaning lower productivity. It generates quite a lot of fumes, needing good ventilation or extraction. And, as we've stressed, that critical need for hydrogen control with certain electrodes and applications.
That's a really clear summary. It paints a picture of a process that's, well, straightforward in concept, maybe simple equipment. But actually achieving consistent, high-quality results requires real mastery. It's not just point and shoot. It really is this kind of dance between the person and the physics of melting metal.
Precisely. It's very hands-on, very reliant on learned dexterity and judgment. And it makes you think, doesn't it? Consider all the welded things we rely on every single day, big and small. Bridges, buildings, cars, pipelines. How much hidden skill and precise control by individuals went into making those joints strong and safe. And how just a small deviation, a bit too much current, the wrong travel speed, choosing a cellulosic electrode when a basic was needed, could potentially be the difference between something lasting for decades or failing prematurely. It makes you wonder what other processes that seem simple on the surface actually rely on such deep, nuanced human expertise when you look closer.